Good afternoon, everyone. Some of you, especially if you're Dutch, may know me from TV, although I do know that the typical age of people watching the 8 o'clock news is 45 years and over, which I notice in everyday life, because whenever I go to a place where a lot of young people are, I can go there unnoticed. But as soon as I go to places where a lot of older people are, then older people are very bad at hiding their enthusiasm. So they usually do, is that the weatherman? So there's a very distinct separation between older and younger generations and being known as a weatherman from TV. So if you don't know me as a weatherman on television, that's good news because I'm actually here as a climate researcher. And I have specialized in climate of the polar regions, so both the Arctic region and the Antarctic region. And these are fantastic places on our planet where temperature is relatively low, at least a lot lower than the global mean. And because we have water on our planet, temperatures are often so low that water freezes. So we have ice in our polar regions, which makes it a very special place to study. I have 2 jobs. 2 days per week I work as a weatherman, 3 days per week I work at university. And in the beginning, so 10 years ago when I started this dual career, so to say, I thought that these were 2 separate worlds, but I have come to realize that both are very much interconnected. And I've come to realize that extreme weather, as we have seen it this summer, for example, but also the previous summers, extreme weather is actually the manifestation of climate change in our daily lives. So meteorology and climatology, they have everything in common. And they are not separate worlds, but they have everything together. And extreme weather, due to global warming, is happening more intensely and more frequently. And that means that with continued global warming, we will start to see the increase in extreme weather unfold more and more. And this year was abnormally warm globally, and we have been kind of overwhelmed by the amount of extreme weather that has come to us. But I can guarantee you that in 30 years from now, we will beg for a summer that was as quiet as this year's. This sets the stage for a lot of doom and gloom, and this was actually not what I intended to do. Because what I'm going to tell you really about is about the polar ice caps or ice sheets of Greenland and Antarctica and also of glaciers. The fact that they are melting and that they are contributing to a rising sea level. And rising sea level is actually, it's like an extreme weather event in slow motion. It's not happening at the scale of days or even hours, but it's playing out on the scale of centuries. And because it's a very slow process, politics tend to kind of, downplay the impact of it. But it's true with what is really true about sea level rise is that the measures that we take now, they will have an impact that will last for centuries. The amount of sea level rise that we can avoid in future centuries depends on the current generations. So, with that having said, I always also want to focus this lecture on how on earth do we actually know how much ice is disappearing? So I also want to focus on let's say, the technicalities, the methodologies that we have developed to monitor the ice sheets that are in such a remote place. It's super expensive to actually go there and take measurements. So how do we know what is happening to these ice sheets? So without further ado, I have to give a brief explanation of the climate system. And you can read the entire IPCC report, which is 3,949 pages. But I'm going to give a 30-second summary. And the 30-second summary is actually here behind me. This is the essential. These are the essentials of the climate system. There's basically 3 knobs that you can turn to influence the temperature on Earth. The first knob that you can turn is this incoming yellow arrow. It's the amount of sunlight that reaches the Earth's surface. And if you turn up the sun, then it becomes hotter, and if you turn down the sun, then it becomes cooler. It's very simple. The second knob that you can turn to impact the temperature on Earth is this second yellow arrow, which is the amount of solar radiation that is reflected back to space. If you would paint the Earth white, it would become much cooler than a black Earth. And then there's a third knob that you can turn, which has to do with the atmosphere. So this incoming sunlight, part of it is absorbed by the Earth, and the Earth emits heat, so long-wave radiation. And this heat has a certain wavelength, and it happens to be that in our atmosphere there are constituents that we call greenhouse gases that exactly absorb this long-wave radiation. It's totally transparent to sunlight, so the sunlight can go through CO2 and methane, etc., etc., but it's not transparent to the heat that is emitted by the Earth's surface. So what happens is that the molecules, they absorb the heat, and then they re-emit the heat again as the molecule falls back to its ground state. But, and this is essential, the emission of long-wave radiation happens in all directions. So upward, but also back down to Earth. And this is the greenhouse effect. The fact that part of the radiation that's emitted by the Earth is sent back by the greenhouse gases. So these are the red arrows. And these are the three red knobs, or the three knobs that you can use to impact the temperature on Earth. So these are the 4,000 IPCC pages summarized as being sun albedo, which is the brightness of the Earth's surface. And here I denote CO2, but I mean all greenhouse gases that we have out here. The Earth used to have large temperature differences in its history, but that was all man-made, or wasn't man-made, it was all naturally caused. And the reason is that the Earth is circling the orbit of the Earth around the Sun. It's not exactly circular, but a little bit an ellipsoid. The Earth axis is tilted, and the tilt is not always constant. And the period in the year at which the tilt is away from the Sun is also changing in time. So these three effects make that at some points in the history of the Earth, there's a little bit more sunlight arriving on the northern hemisphere in summer than in other periods. And there is some periodicity here. So every 20, 30, 40,000 years, we have a little bit more sunlight and a little bit less sunlight arriving on Earth. And this has been the driver for ice ages in the past, well, a little bit over 1 million years. And, well, about 12,000 years, we were at the maximum of the last ice age. Back then, the ice didn't reach the Netherlands. That was true in the ice age before the last one. That was about 120,000 years ago. Then the ice sheets came all the way from Scandinavia to the Netherlands. And, well, here in Eindhoven, you cannot see any remnants of it because the ice sheets, they ended at the Veluwe, more or less. So all the hills that you see, the Utrechtse Heuvelrug, so it's close to Utrecht, and also the Veluwe, those are remnants of debris, rocks that were pushed forward by the ice sheet and ended up there as our Dutch mountains. This is what Europe must have looked like approximately 12,000 years, so during the last glacial maximum. And the ice didn't actually reach the Netherlands, but there are two peculiarities about this map, which first of all is this enormous white blob, which is the ice sheet that used to be in Northern Europe that is no longer there. And it was in the center here, it was about 2 to 3 kilometers thick. So it's really a lot of ice. So that's the first striking thing about this map. And the second thing is that, well, if you would end up at the coast here in the Netherlands, you could walk all the way to the UK, say hi to all the mammoths that you see on the way. And the reason that you could do this is that the North Sea is very shallow. It's only 10 to 30 meters deep. It's not really a sea. We are very proud of the North Sea, but it's basically just a basin of lukewarm water. The real ocean starts here. And this ice had to come from somewhere. It was evaporated out of the oceans and then deposited on the continent to form a 3-kilometer thick pile of ice. And this amount of ice was so big that global mean sea level was about 120 meters lower than today. The Earth, we know, in the last glacial maximum was about 5 degrees colder than now. So we can do very simple arithmetics and say, okay, 120 meters of sea level for 5 degrees of warming. That means 24 meters of sea level rise per degree of warming. Yeah, okay. So in Paris, we agreed on 1.5 degrees of warming since the pre-industrial period, so that's 36 meters of sea level rise. That's what we are committing to. Or are we? Yeah, that's a good question. It has to do with timescales, and I'm going to come back to this. So this is what the Netherlands must have looked like approximately 12,000 years ago. One big tundra, like what maybe northern Norway looks like nowadays. And the ground was frozen. It was permafrost. So we had a big ice sheet on Scandinavia 12,000 years ago, and we had an equally big ice sheet that was on top of North America. So mainly Canada and parts of the United States. At the moment, we only have 2 of these ice sheets left. And the first one is this one. It's the Greenland ice sheet. It's not this. Journalists are often confused about this. But this is not an ice sheet. This is frozen ocean. The ice is maybe 1, 2, 3 meters thick. The salt has been ejected from the ice, so it can freeze. The freezing point of the ocean is lower than 0 degrees because of the saltiness of the water. But this is floating ice on an ocean. This is an ice sheet. The center of the Greenland ice sheet, there the ice is about 3,500 meters thick. And that's one of the ice sheets that we have left. The other ice sheet that we still have is the ice sheet on Antarctica. So suppose that we would melt the Antarctic ice sheet in its entirety, and we would add the water to the ocean. Who of you thinks that sea level would rise by more than 1 meter? Who would think that sea level would rise by more than 10 meters? Who thinks that it's more than 50? Who thinks it's more than 100 meters? A kilometer? Oh, 1 hand still. Oh, brave. Oh, 2 hands. 2 hands. Very brave. That's very brave. It's very difficult to get a scale because this is about 25 million cubic kilometers of ice that is lying there. But how do we translate that to sea level rise? I'm going to show you, not in this slide, but in a few slides, so you will get the answer later on. Suspense. Okay, so these ice sheets, they can contribute to sea level. That's one of the reasons why I and my colleagues study them. But there is another reason, and that is that the ice sheets, they provide a fantastic archive for past climate change. And it works like this. How does an ice sheet form? There is snow falling in winter, and then in summer, part of this snow is melting away, but at the end of summer, there is still a little bit of snow left. And then the next winter comes, and it dumps another meter of snow. And in that way, layer upon layer accumulates and gets buried. And under its own weight, the snow is slowly compressed to ice. And that's how an ice sheet forms. Snow is a mixture of ice crystals with a lot of air in between. And the air actually gets compressed into the ice as bubbles. And what we can do is we can extract an ice core, so it's like a cylinder of ice that we drill into the ice, and we extract it like this. And what we then can do is that we analyze the atmosphere, so the air that is inside the bubbles. It's old atmosphere. So we can study CO2 concentrations, methane concentrations, particles, dust, aerosols, everything that we want. We can extract it from the bubbles that are still preserved in the ice sheet. And the lower you go, the older the bubbles. The only thing you need to do, which is like a science in itself, but I won't digress on it, is that we have to know what age it is. So you need an age scale for it. So this is one thing that we can do. The other thing is that the way that the ice is actually formed, it has to do with isotopes. It tells you something about the temperature that we have on Earth. And in that way, we have like a co-registered archive of global temperature and CO2 and other atmospheric constituents. So it gives us a very good idea of what the role is of CO2, greenhouse gases, on the Earth's climate. And it gives us a picture of climate up to about 800,000 years ago. So in very much detail, we understand nowadays the climate of the Earth in the past 100,000 of years. And this is an example of the results that were recovered from an ice core that was drilled in Antarctica, where we have the oldest ice, up to 800,000 years old, and at the moment there is a quest for 1 million year old ice. And this is ice which is buried very deep, so it's at 3.5 kilometers below the surface. The drilling of such an ice core, it takes typically 4 or 5 Antarctic summer seasons. So you build a camp, then you drill the first kilometer or so, which goes very fast because you lower the drill and then it goes back up. But the deeper you go, the longer it takes to get another 5-meter piece. You have to lower the drill by 3.5 kilometers. So you sit there and drink coffee. It's not me who has ever done it, but that's the story that I hear from colleagues. So you sit and drink coffee all the day, all time, because it takes a lot of time to retrieve the lowermost pieces of ice. But they do contain a lot of information per meter because the ice is compressed so much that, like in the uppermost few hundred meters, 5 meters of ice is maybe 50 years of climate data. But low in the ice sheet, the same 5 meters of ice may contain thousands and thousands of years of climate data because the ice is so much compressed. So it takes a long time to get the ice, but it's very rich in data. So this is what we get. If we analyze the CO2 in the air bubbles, this is typically what we get. We have high periods of high CO2 concentration and low CO2 concentration. At the moment, this is actually an old picture because we are now at 420 parts per million. So about exactly 50% above anything that we have recorded in the past million years. This is the temperature that we reconstruct from isotopes in the ice surrounding the air bubbles. Well, there are periods that are warmer, which we call interglacials, so periods without an ice sheet, and colder periods, like this one, which we call the ice ages. And lo and behold, there is a correlation or a simultaneous occurrence between high CO2 concentrations and high temperatures. But the question is, which is the chicken and which is the egg? Well, we understand now how that works, and it has everything to do with Coca-Cola. Because why is Coca-Cola so much better when it's cold than having a lukewarm Coca-Cola? Yeah, the CO2. Yeah, there's a lot more bubbles in cold Coke than in warm Coke. The oceans in an ice age, they are like a cold bottle of Coke. They can absorb a lot of CO2, which is taken out of the atmosphere and going into the ocean. In a warmer period, the CO2 is outgassed into the atmosphere. So we have an atmosphere that contains a lot more CO2. So what happened? Now we understand what is going on. The Earth is revolving around the sun. It does so a little bit irregularly, which causes more or less sunlight to arrive on Earth, which is the driver for past climate change. How did the CO2 levels go up and down? It's because whenever it was warmer, so there was more sunlight on Earth, when it was warmer, the oceans, they started to emit CO2. And the CO2 acted to increase the effect of the Earth being closer to the Sun. So it's a chain of processes that reinforce the initial warming coming out of an ice age into a warmer period. And also the other way around, whenever the Sun is getting a little bit further from the Earth, the oceans start to cool. They take CO2 from the atmosphere into the ocean, which enhances the cooling. And then there is a third effect, which I didn't even mention here, is that the growth of the ice sheets, they cause the Earth to become whiter, which reflects even more sunlight and makes the Earth even cooler. So there are a lot of positive feedback processes going on in the Earth system that makes very subtle changes, like just a few watts per square meter more or less sunlight, result in the difference between very warm periods and very cold periods. So what the history teaches us is that the climate system is extremely sensitive to disturbances. Okay, I'm getting a little bit thirsty from showing a bottle of Coke for a minute. So welcome now in a totally different era of the Earth's history, which is that no longer the Earth is turning this knob by itself, and all the other knobs are... So what is basically going on, so what has been going on in the climate system, is that these knobs are not just three knobs, but they are connected on the backside. So once you start to turn this knob, which is what nature used to do, the other knobs are also going to turn by the ocean and by the growth and the demise of ice sheets. So in the back, turning one knob means also turning the other knobs. Now we have a very interesting, problematic situation, which is that 150 years ago, we discovered the power of fossil fuels, and we started to burn them, and as a waste material, it gives you CO2. And the waste cannot go anywhere except for to the atmosphere, which means that atmospheric levels of CO2 are now rising. So this knob, we are now turning ourselves as humans. And the question is, how are the other knobs going to respond to this? Well, this knob turns out to be totally insensitive to turning this knob. So there is not much, there is little changing in the amount of sunlight that is arriving on Earth, at least in the past 150 years. There are minor effects. For example, now that we are using diesel and fuels, we are also emitting dirty particles, which shield off a little bit of the sunlight arriving on Earth, but it's a very minor effect compared to the greenhouse effect of the CO2 itself. It's at most 10% of the greenhouse effect itself. What is going on in the polar regions is that now that we are turning this knob, we are also seeing changes in the albedo of the Earth. The polar regions are getting darker. And it's the exact reason why climate change is enhanced in polar regions. It's because a bright surface of sea ice and of snow cover in Antarctica or in Siberia, for example, or in Canada, is replaced by a very dark surface of tundra or open ocean. So white becomes black, more radiation is being absorbed locally, and it enhances the temperature increase in the polar regions. So this is what is going on at the moment. The amount of CO2 is steadily rising. We are now at a little over 420 ppms, which is 50% more than before the industrialization started. And this is the growth rate. So the amount of ppms that are added each year. So it's the first derivative. And also this is increasing, which means that every year more CO2 is added than the previous years. We seem to be at a point where the first derivative is leveling off, which means that the increase is not increasing further, which is the first step towards seeing a demise in annual emissions, which is the first step to leveling off the CO2 concentration in the atmosphere, which is what we aim for in a little bit less than 30 years from now. As a consequence of the greenhouse effect, which we understand very well thanks to the ice sheets, temperature has also gone up on Earth by on average about 1.1 degrees, but that includes oceans. Oceans take up about 70% of the Earth's surface, a little bit more, 71%, and they warm up a lot slower than the continents where we live. So if we would only take the area where we humans live, then global mean temperature has gone up by between 1.5 and 2 degrees already, depending also on the continent where we live. So how do we know that it's actually greenhouse gases? Well, there is really a lot of evidence that the current global warming is caused by greenhouse gases. But let me give you one example, which is running climate models. And we include the effect of greenhouse gases onto the simulated temperature in climate models. And then we do increase the amount of CO2 in the models, and we don't increase. And we have like a control experiment. And this is the result. This is the control experiment with no human influence. You see that the temperature stays constant. And with increasing CO2 levels, we see temperatures increase. So the best guess that we can make how much of the current global warming is caused by human interference is 110% of the warming can be explained by CO2. Whoa, that's more than 100%. How possible? It's because without any human influence, the Earth would have very probably cooled by about 1/10 of a degree. So it's the entire warming signal plus a little bit more that can be explained by human action. Okay, so the next step is that sea levels are also rising due to the fact that the temperatures on Earth are increasing. Nowadays, we can measure the Earth's surface height by satellites. And from these satellite observations, we see that, and these satellite observations are available since about the 1990s, we see that sea level is going up. Longer back in time, we can look at tide gauges, which are these, when you are in a harbor, you can see what the tide is. It's like 3 meters, 42 centimeters above a certain reference level, for example. And these data have been available since forever. Well, not forever, but since, let's say, the 17th century, approximately, when shipping really took off and people started to note, the tides in big logbooks. So if you reconstruct all those data from the 1700s onward to present day, you can make a reconstruction of global mean sea level as they are recorded by tide gauges in harbors around the world. And we can do so reliably since about 1880. And then we can make a reconstruction of global mean sea level, if you average out all the tides and then all the annual effects, which is currently about 25 centimeters of sea level rise that we already had, with large spread between places on Earth. And what we see is that it's accelerating. So over this entire period, the global mean rate of sea level rise is a little under 2 millimeters per year. But in about the last 15 years or so, the rate has been about 4 millimeters per year. So double the average rate over the past 125 years. Okay, who has ever been on a glacier? Who has actually ever hiked on a glacier? Okay, cool. Who has ever been to Greenland? Whoa, who has ever been to Antarctica? One. Whoa, lucky you. Yeah, so you have seen most of the ice of all the people here in the audience. That's great. But how much was it? How much ice did you see? We're going to find out soon. So this is what a typical glacier looks like, and the glacier is actually a perfect model for understanding what an ice sheet is. So high in the mountains, it's relatively cold, and there is more snow falling than there is melting in winter. So we have accumulation of snow, the snow compacts to ice, and ice is a fantastic material. It's a so-called non-Newtonian fluid. For those who are into fluid dynamics, they understand what I mean, and for those who don't, it doesn't matter. But what happens is that the ice is not just a solid, but it deforms under the act of gravity. So it's being pulled down, just like glass. Like if you have glass-stained windows in old cathedrals that are 800 years old, you see that the glass is actually, over the course of 800 years, it's slowly dripping down very slowly, but it's happening. I mean, if you go to very old churches, the bottom part of the glass is thicker than the upper part. So it's flowing, but slowly. The same is happening with glaciers, although a little bit faster than with glass. And the typical speed of ice in a mountain glacier is about 50 meters per year. So that equals about 15 centimeters per day, which is, well, not a lot, but certainly not negligible either. I mean, if you would go and sit there and have a beer sitting next to a glacier, you could sit there all day, but you would see nothing happening. And if you would see something happening, it would probably be because of the beer. So this is the ice that is flowing down, and at some point it gets into the valley, and in the valley it's so warm, it's a lot warmer than high in the mountains, which means that more ice is melting than snow is falling, which means that there is also an end to this system. So we have a closed system with input, transport, and output of mass. That's the way that well, if you have a physics background like me, likes to look at such a system. So the transport can be enormous. This is one of the biggest glaciers that we have outside of Greenland and Antarctica. This is in Alaska. This is 9 kilometers. This is 55 kilometers. So it's really giant highways of ice, which also show to be very effective in shaping the landscape. Because here at the junctions of glaciers, simply the rock is being eroded and carried on this highway to the end of the glacier. So we actually see we see natural transportation power in action, and this is actually the way in which mountain landscapes are being formed around the world by glacial action. It's by far, apart from nowadays human activity, it's by far the most efficient way of landscaping in the world. Here's another picture. I don't have a story with this picture, it's just very nice. And so those are all the mountain glaciers that we have. And we have more than 200,000 of these mountain glaciers. So really a lot of them. Most of them are in places where we have actually never been, like Arctic Canada, the Himalayas, Arctic Russia, the islands around Antarctica. Those are the places where we find the largest, the biggest, and the most of these mountain glaciers. So then we have this ice sheet that we already mentioned, and then we have the enormous ice sheet of Antarctica. So, how much ice is there? Finally, an answer to this 1 meter, 5 meter, 10 meter, 1 kilometer of ice. If we take all these 200,000 mountain glaciers and we would melt them in a hypothetical experiment, the experiment is actually not so hypothetical at the moment, we find out that approximately the volume of all these glaciers is about 170,000 cubic kilometers, which equates to about 40 centimeters of sea level rise, which is something that we can deal with, right? I mean, we put up some dams and we give some money to Bangladesh and other regions who don't have dams, and then we can deal with this issue, right? Okay, then we have Greenland, which contains 3 million cubic kilometers of ice, which is equal to about 7.5 meters of global mean sea level rise. But this is again being dwarfed by Antarctica, which is good for 56 meters of global mean sea level rise. So this is the reason why me and my colleagues actually bother about what is going on in Antarctica, because 2% of all this ice is a little more than 1 meter, and it's an incredible problem already for the Netherlands. So what we are interested in is, okay, so from a scientific point of view, if the temperature on Earth would rise by 3 degrees, suppose that it happens, then the answer, what is happening tomorrow, is very simple, more or less nothing. The question what the world will look like in 20,000 years from now is also very simple, because sea levels will be 60 meters higher than today. But the question, and this is like really the holy grail in glaciology, is what is the world going to look like with 3 degrees of warming in 100 years from now and 200 years from now? So the problem in this question is not the equilibrium state, because we know exactly what the world is going to look like with 3 degrees of warming in 20,000 years from now, But the problem is in the transient response of the ice sheets. So what is going to happen with the ice sheets, and how long does it take for them to melt? That's the big question. And that's where all the uncertainty comes from. We know very certain what is happening very far away from now, but we don't know exactly what the ice sheets will look like in 100 or 200 years from now. We don't know. So how do we measure them? Okay, so we have 4 millimeters of sea level rise. I'm going to tell you that about half of it, so 2 millimeters of sea level rise that we observe now, has nothing to do with ice. It's just due to the expansion of ocean water. So the ocean is getting warmer. Warmer water takes more volume, so the density decreases. The ocean is about 4 kilometers thick on average, but at the moment it's not 4 kilometers thick, but 4 kilometers and 10 centimeters. Yeah? So that is 50% of the explained sea level rise signal that we, as we know it. So which means that the remaining 50%, so 2 millimeters per year, it's an ice signal. But how do we know? And how have we developed measurement techniques that can take a body of ice, which is good for more than 50 meters of sea level rise? How can we know that it's contributing about 1 millimeter of sea level rise per year? It's so super accurate. It's like me going to the general practitioner and say, oh, I want to lose weight because I'm not feeling so well. I should work on my body mass index. And then he says, okay, go put you on a scale, and it says, okay, your weight is now 80 kilograms. Come back a year later and see if you succeeded in losing weight. And then 1 year later, I would come back, I would go on the same scale, and he says, wow, your weight is now 79 kilograms and 999.5 grams. You succeeded in losing weight, great. That's the accuracy that you need in weighing an ice sheet. So how do we go about? The most elegant way, and it's an invention made by Germans, always Germans, they come up with great ideas, and it's actually using gravity. And how do we do this? We do this with satellites. So now I'm going to explain to you, I know that you all have good grades on physics, otherwise you wouldn't be studying on a technical university, but still. Okay. What I'm doing now is showing you the power of gravity. Here we go. Yeah, so what happened? What happened? I was pulled back by the Earth. Yeah, that's the thing that you saw, but what happened else?
The Earth was pulled up to you.
Yeah, the Earth was pulled up by me. Yeah, the crucial thing about gravity is that it's a force that always has two sides. So equal and opposing forces. That's also in the form. I don't have the formulas here because I hate formulas in presentations, but you get the idea. There is an m for the Earth, the mass of the Earth, and in the equation is also my mass. But to make it a little bit simpler, we ignore one of the terms because it's so much smaller than the other. But in the original term, there is two mass terms in the equation of gravity. So there's two things happening here. The Earth is pulling me down, and as I jump, I'm also pulling the Earth up. Great. But how can we use that to our advantage? Okay, now I'm going here, and now we're going to assume that this desk over here is an ice sheet. And we have two satellites. They are separated by about 220 kilometers. This represents a lot of mass, okay? So these two satellites, they are flying orbits around the Earth, and then now the first satellite comes a little bit closer to this mass. So what happens is that it's being accelerated a little bit to this pile of mass over here. So the distance between the two satellites is increasing. Yeah? Now the second one is also being attracted to this mass, so it's also accelerating a little bit, which means that the distance between the two satellites is decreasing again. So by measuring the distance between the satellites and the changes in them, we can map the gravity field of the Earth. And this is a very precise observation. It has to do with phase locking of lasers. Some of you may know more about it even than I do. But you can measure with about 1 micrometer of accuracy the distance between the two satellites, which are 220 kilometers apart. Because it's not actually the actual distance that you measure. Some of you may know this, but you're actually measuring the changes in the number of waves of the laser light between the two satellites. And that you can do very accurately. But it's still a technical feat that we can be so accurate, and it's the accuracy that we actually need in order to map the gravity field of the Earth. So that's one method that we can use to measure the ice sheets and how they change over time. The second way that we can use is what we call altimetry. And altimetry is basically nothing else but making a 3D scan of the Earth's surface with a laser pointer mounted on a satellite. So we basically measure the two-way travel time of the laser light going from the satellite to the Earth and then reflect it back to the satellite. And then we make a 3D scan. And then we come back a year later, and then we subtract the two scans, and then we know where mass has disappeared. Or to be more precise, where volume has disappeared. Because all that we measure is volume changes. But what we are interested in are mass changes. So we need to convert, and we need the density for that. So one of my specialties, and it's very much detail, so it's too much detail maybe for this lecture, is that, well, the density changes, they can be due to the fact that the ice has disappeared on ice sheets, which has a density of 917 kilograms per cubic meter, or some of the snow may be blown away, right? And snow has a density of 250 kilograms per cubic meter. So my particular job at the University of Utrecht is to make models of the snow layer covering the ice sheet and try to model the changes in that snow layer. And then we can subtract that from the observed volume signal, and then we can know what the mass change is that belongs to the volume change that we measure by satellites. Whoa, great. You can build a career onto this. Okay, so and then there is a third way, which I will skip for now, just for simplicity and also for time's sake. But basically what you're doing is just bookkeeping. So you're trying to see how much snow is falling. We do that with, now I'm going to explain it anyway. So we do that using weather models, but we don't do it to predict weather, but to reconstruct weather into the past. So that gives us a record of snowfall. So then we know how much mass has been added to the ice sheet. And then we count the number of icebergs that are breaking off from the sides. And we subtract those two really big numbers. And the difference between these really big numbers is a very small number, but that's the mass loss in a year. So it's bookkeeping that we do. I'm skipping all of this because I'm running out of time. But what is becoming clear, especially for Antarctica, is that there is one area here, which is what we call West Antarctica, that is losing mass. Everything red is mass loss, and everything blue is mass gain. So there's a few places where we have more snowfall than icebergs breaking off, but we have a lot of places where there's actually more ice disappearing than snow is being added. And that leads to a net loss of mass on the ice sheet of Antarctica. We think that we understand why. It has surprisingly little to do with global warming. Global warming is the dominant effect for the melt of all the mountain glaciers in the world, also for large parts of the melt of the Greenland ice sheet, but for Antarctica it's a slightly different story. This is an area where the ocean water has become warmer, and the ocean is actually able to eat away the ice from below. And this is exactly what is going here. So the ocean here plays a very important role. Now the next question is, okay, why is the ocean warming? Yeah, so it's a very long story. All in all, it has to do something with global warming, but it's more delicate than just, okay, it's warmer, so the ice is disappearing. Okay, so what about the future then? This is where the uncertainties start to play a role, because the Antarctic ice sheet is losing mass, but it's super difficult to extrapolate the observations that we have now into the future. And if you go and read the IPCC reports in detail, you will read that the contribution of the Antarctic ice sheet is potentially enormous, but fraught with big uncertainties of 1.5 orders of magnitude uncertainty. So it's really, really a big problem that we need to tackle as glaciologists, try to understand more of exactly that ice that is so far away and so difficult to reach. So we have uncertainty bands when it comes to extrapolations of sea level rise into the future. But one thing we know as glaciologists with a little more accuracy or with a little bit more confidence than, let's say, 10 years ago, which is that it matters a lot what path of global warming we are going to take for the ice sheets and for sea level in the coming centuries. This is a very optimistic path, so Paris Agreement, etc., successful climate policies. And then we have a little under half a meter of sea level rise by the end of the century. And it will stay under a meter of sea level rise even in the next centuries to come. This is a path of unlimited use of fossil resources. Then we will see a meter or even more of sea level rise by the end of the century. And the striking thing is then the acceleration has just started. So from then onward, we will see more and more change. This is a distinction that we can make now that we weren't so confident in about 15 years ago. And this is, well, in effect, this means that there is an end to the time that we could live in the Netherlands. By the year 2200, the sea level will have risen by so much that probably we will have to move elsewhere. There's a lot of stuff that I'm going to skip for sake of time. I'm not going to say anything about this. Ask me questions about hydrofracturing. I'm happy to explain it to you. I'm going to skip all this, and I'm going to wrap up with some main points. Most of them I already explained, but what I wanted to give you as takeaway is that the present-day warming is really unequivocally caused by human activity, and as a result, sea levels are rising and, at the moment, accelerating. The future of sea level rise is uncertain, and it has mainly to do with Antarctica. I mean, so the mountain glaciers, they contribute, if you would all melt them, they would contribute about 40 centimeters, but we think that we understand very well what is going to happen with them in the future, even though there are so many, they are in so many different continents, but they are relatively easy to understand. The big problem is with Antarctica, which has influences from both atmosphere and from the ocean below. It's a very fragile, it's a very difficult, complex system to understand. The marine parts of Antarctica, so the parts of Antarctica that are actually floating in the ocean, they lead to the largest uncertainties, and they are the main reason why still after decades of climate publications, we are not sure whether by the end of the century, sea level will have risen by 80 centimeters, 1 meter, 1.5 meter, or maybe even 2. So thank you very much.